Whew, okay, so questions in the test. Wanted to make sure to go through some of these and showcase kind of how we're going to look at some of these test problems and some tips, some tricks, some strategies you can approach, as well as review some of the pieces that we may have forgotten from this particular chapter. So let's get started. For question number 1, we've not had to do any that involve variables in the integration where you have an unknown. And so having this integral going from 0 to k is a little unique. So you have the integral from 0 to k of 2kx minus x squared dx equals 18. Now, the trick to this is, whenever you look at this problem, remember k is a number. It is just a number. So this is like 20. Okay, it's just 2k. And so you can solve this problem by using basic integration and then plug in 0 and plug in k. The only trick will be you already know what the answer should be. The answer should be 18. So let's look at a similar problem. So let's go from 0 to k. Let's say of 2kx minus, let's say, 6x squared. And let's say this is equal to, 20, whatever it happens to be. So I changed two numbers, giving you a similar example. Well, let's take a look at what happens to this problem. Well, if I do the integral, so remember, 2 and k are numbers. X is the only thing that's going to change. This would become 2kx squared, and then have to divide by the new power, which is a 2. Minus 6, x squared becomes x cubed. I have to divide by the new power, evaluated from 0 to k. So let's simplify this. So the 2 and the 2 are going to cancel, leaving kx squared. The 6 and the 3 are going to cancel, leaving me with just 2x cubed, evaluated from 0 to k. At this point, I can now plug in 0 and I can plug in k, which is what I'm going to do. So I plug in k, I get k cubed minus 2k cubed. That's the first piece. Minus k times 0 squared minus 2 times 0 cubed. And then from here, I get the following solution. So k cubed minus 2k cubed gives me negative k cubed. And then 0 times k is 0, 0 times 2 is 0, 0 minus 0 is 0, and minus 0, which means I just get negative k cubed. And the question becomes, okay, this is going to equal 20. So this whole time, we know it's supposed to be equal to 20. We know it's supposed to equal 20. We know it's supposed to equal 20. We know it's supposed to equal to 20. So now we can actually take the time to find the solution by dividing by a negative, give me k cubed equals negative 20, and then taking a cube root. So for my example, k is the cube root of negative 20. So all you do is the same basic process as before, just you have a k involved, and you already know what the solution is. And so when you're finished, you have to make your equation equal to the number, and then solve for the k. That's the big difference between this and previous problems. So there's number 1. Let's look at number 2. Which of the following integrals is and are true if f of x is a differentiable function on the open interval such that the following is true? So we have a and b, where c is in this interval. So if you think about this in terms of a number line, you'd have a, b, and c in the middle. Okay, where is that in the middle? Doesn't really matter that much. It could be close to a, it could be close to p, doesn't matter. This question, number 2, is a properties question. There are properties listed in the textbook about how to do integrals when you know the properties. And one of them involves combinations and then setting them apart. So for this example, I want you to note specifically what 2 components are on this function. We have the integral from a to c of f of x dx being defined as a number, 6, and the integral from from C to B of f of x dx. Now what this tells you is this interval is from A to C. The other one is from C to B. So if you remember your properties, we can put these two together to tell the entire interval from A to B just by using addition. There are other things you can do, though, that would also get you similar answers, which is why for this one, there are the number 2 and number 3 are also possibilities. So I will tell you straight up, number 1, or I, is true. But it may or may not be the only one. You need to check the others using the properties. That's a big detail that you have to know. You have to check the properties to use the other ones. Or scratch that, reverse it. You have to check the other ones using the properties that are listed in the textbook about these particular functions. And pay careful attention to the bounds. Because if the bounds change, then your solutions change. Some of your answers go from A to B, some go from B to A. And so you have to be very conscious about which one's which, because that will change the solution. So here's number 2. No similar example, but at least a nice little explanation about where that question comes from. All right, number 3. There we go. Let's remember our definition of a Riemann sum. The definition of a Riemann sum is you're supposed to take f of x times delta x for each delta. Now, we spent a lot of time talking about when delta is a constant. Remember, delta is just the width of each rectangle. So if you look at this problem, they've defined this nice little setup. We have the first point is 544. The second point is 1312. Then we have 22, 13. (27), 17, 35, 22. Okay. So remember, your delta is defined as the difference between these two values. So remember, these first two represent the first rectangle. These next two represent the second rectangle. The next two, the third rectangle. And these last two, the fourth rectangle. And so if you want to know what the delta is for this first rectangle, the delta is just the distance between the two. So in this case, our delta is found by taking the two numbers that are x's and subtracting them. This tells me that for my first one, my delta is 8. However, my f is defined in one of 3 ways. The f could be defined as, say, the left hand, the right hand, or maybe even the trapezoidal. If it says the left-hand one, then of the two values, we got to choose the left-hand one. So if it said, for example, if it said find the left rectangle, we'd make our f of x equal to 44. If it said do a right one, we'd make f of x equal to 12. That's just for the first rectangle. And so notice that the delta is pretty consistently 8. But how tall it is depends on whether you're doing a left one or the right one. And the problem tells you which one to do. You just have to look very carefully. For the second rectangle, similar process. Again, we find delta x. We would do 22 minus 13 which is 9. And next one, our f value, again, would depend on whether or not it is the left or the right. If it mentions the left one, for this second rectangle that includes these values, the left-hand value is 12. The right-hand value is 13. So if the question said, hey, find the area of the first rectangle, if it said left, we would do 8 times 44 and get an answer. This would be the left Riemann sum. If it said the right, we would take 8 times 12. To get the right Riemann sum. For this one, if we said find the left Riemann sum, we would take 9 times 12 and get an answer. If we said the right one, we would do 9 times 13 because it is the right value of the 2 for the second rectangle. Now, if the question says find the Riemann sum for the entire distance, we got to do this for all 4 rectangles. And so there are your components to find number 3. When it comes to a Riemann sum, remember, you have to know 2 pieces, f of x and delta x, and you have to multiply them. So the question becomes, what's f of x, what's delta x? Delta x is the easier of the two. It's just take the x values and subtract them. F of x for the other one is different because it could be the left value, it could be the right value. We also talked about max and min Riemann sums, where we always choose the larger or the smaller value. You have to pay attention to what the question asks for to know which one is which. Okay, number 4. At 10 a.m., the temperature of a ski resort begins to increase, causing the snow to begin to melt at a rate defined by this equation. M of t 10 plus 8 cosine of t over 3. If there are 178 cubic yards of snow at the point, how much snow remains at 5 p.m. if no additional snow has been added and the temperature hasn't continually increased throughout the day? Okay, so a couple things to point out here. Number 1, we are given the rate of change. If we integrate the rate of change, we will determine the total snow, or the total cubic yards as referred to in the problem. So, what this problem is saying is to integrate this function. What it's also saying is at the beginning of the day, it is at 178. What this 178 tells you is called an initial value. What that means is when the time is 0, you have 178 cubic yards of snow. So what that tells you is that this function has a value. So when we solve this thing, we're going to get a new function. Let's call that snow. Okay? That snow is going to be an equation. It's going to have a plus c in it. Okay? So it's going to be some weird equation. It's going to have plus c in it. What we can do is we can actually use this to find c. And then once we find c, we can plug it in and get the actual equation. Because remember, this right here is a general form. Whenever we solve it, it's going to have plus c in it. We're actually going to be able to find the actual form by using this to find c. This was done, I believe, in section 4.3. So if you need a little bit of a refresher, take a look back at section 4.3. It should have some examples that go case how to do this with basic integrals, which is what this is. The last component of this is the weird part because it specifically states find it at 5 p.m. So at 5 p.m. something unique happens. At 5 p.m. So at 5 p.m. that is 7 hours later. It wants to know what number do we get. So once you find this answer, once you get this equation, you need to plug in 7 and see what the answer is. So, one last time. We're going to integrate the function first, getting the new function that's going to have c in it. We're going to use the initial value to find out what c is to get the actual equation. And once we have the actual equation, we're then going to plug in our number to figure out what the new total is supposed to be. So, there it is. There are a few things to help out with this problem. You can actually tell the answer B doesn't make any sense if you just look at it from a realistic sense. You're starting with 178 cubic yards of snow, and then it begins to melt. So if it's melting, that means there's less snow. If there is less snow, then that means the number of cubic yards of snow is going to go down, which is why B makes no sense. How did we get more snow? It doesn't make any sense, especially since this is the problem. No additional snow has been added. It's only been melting away. So for number 4, note the process. We first integrate to find the total snow formula. That's what we call S of t. We then plug in the initial value to find C, getting the answer, which I believe is covered in section 4.3. And once we have that equation, we then plug 7 in and get an answer. Okay. 4 is probably one of the most difficult ones we have on this test, just because of the sheer volume of work. You have to find S of t, then you have to work backwards. It takes time. All right. Next. Number 5. Number 5, it says we have if f of x from 0 to 3 is equal to 6 and from 3 to 5 is equal to 4, then find this new value. Okay. To find this new value, this, much like number 2, is a properties question. There are multiple properties listed, I believe, also in section 4.3 that showcase how to do this with just the properties. Remember, one property you should know. You have the integral from a to b of, let's say, m plus n dx. If that's the case, you can always split these from a to b of m dx plus the integral from a to b of n dx. So that's one of the properties you have. And the second property is the combining property that you're saying you use in number 2. And so this is the big one for this problem, is remembering that you can always take these integrals that are written in one form and split them apart. You can do that for the function they've given you in the end to split it from 3. You can also do it with multiplication. So you have the integral from a to b of kx dx. You can rewrite that as k on the outside, integral from a to b of x dx. You can essentially factor the k out because it's being multiplied. And so these are the two properties that you're going to use the most in number 5, and there they are. So, number 6. Number 6 is a second fundamental theorem of calculus question. The second fundamental theorem of calculus states that the integral and the derivative cancel each other out, which is really important. And so you need to make sure to always find those pieces that can cancel each other out for number 6. We have here g of x is equal to an equation, and we have fx equal to g of x prime, which means if we do a direct substitution, this tells me that the integral of 3 to 1 would be g prime of x, and integrals and derivatives naturally cancel. Thing is, what happens when we actually do that to these numbers, 1 and 3? Okay, number 7. The graph to the right is a graph of the derivative of the function. If f equals 0, what's the value of f of 2? So, when it asks you where the value of f of 2 is, we've been given an initial value. We can actually find the area. Remember, the area is going to be the f function. And we can use that to determine what the actual area of this space is. So, number 7, fun one. Just going to make sure to find the area. Number 8. It lists three different methods. It says a left Riemann sum, a right Riemann sum, and a trapezoidal sum are used to approximate the value from 0 to 1 of this function. Each use the same number of subintervals. That's a big detail. The graph of the function f is shown the figure to the right. Which of the sum givens are an underestimation of the value of f of x? So for number 8, it's really important to look at this picture. Let's look at this graph. Okay, from 0 to 1. Okay, if I look at the graph, let's talk about the three things that can happen. We can have a left Riemann sum, which I'm going to do here in purple. We can have a right Riemann sum. And we can have a trapezoidal. So let's look at those three. So to do this, I'm going to break this up into a couple different intervals. I'm going to do this in terms of, let's see, I think I'm going to do it in terms of just 2. That'll be nice. Okay. You can do it with more intervals. You can even do it with less, and it makes just as much sense. Okay, let's talk about what the left-hand one would look like. Well, we'd use the left-hand value of this first interval. So that tells me that this would be the left Riemann sum for the first rectangle, and the left Riemann sum for the second rectangle. Notice that both of these are too small. So that tells me the left one, oh, damn it, change the colors. Left. Should really grab the right color pen. Okay, my left one, this is too small. If I compare this to the right one, the right hand one for this first rectangle is going to use the right hand value, which is over here, which tells me it's going to use this piece, and the second one is going to use that piece. As you can see, this one is too big. If I use the trapezoidal method connects the two endpoints together. So to use that one and this one. Remember, the actual area is between the curve and the axis. So you know how it's missing some? This tells you it is also too small. With this information, you should not be able to answer number 8. In fact, I've given you pretty much everything you need to answer number 8. Alright, last one. The free response. Using the midpoints of 5 subintervals of equal length, approximate the value of 0 to 30 Vt dt. Using the correct units, explain the meaning of the value of this integral. Okay. Let's talk about some things. First of all, we have to use 5 subintervals. Now, notice they've given me more than 6 values. They've actually given me what appears to be, 13? 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, I'm sorry. They've given you enough because you need to choose in midpoints. So, it's the last one. We are given this nice little table of t and v of t. We have 0, 3, 6, 9, 12, 15, 18, 21, 24, 27, and 30. Those values 0, 7.5, 10.1, 12, 13, 13.5, 14.1, 14, 13.9, 13, 12.2. It says in the problem, oops, sorry, on this page here, just copying the table down. It says in the free response, use the midpoints of 5 subintervals of equal length. So I got to take these lists and create 5 intervals. Now to do this, let's go ahead and take a look here. I'm going to choose this to be 1 interval, this to be 2 intervals, 3 intervals, I'm dumb. I'm dumb. So God, I'm dumb. Okay. That isn't working at all. Let me try that one more time. Because I'm skipping some numbers here. Okay, let's try this again. From 0 to 6, I'm going to declare as my first interval. Goes from 0 to 6. Now from 6 to 12, I'm going to declare as my second subinterval. From 12 to 18, I'm going to declare as my third. From 18 to 24 as my fourth. My fifth from 24 to 30. Let's first make sure this is allowed. Before I go any farther, I have to make sure I have all these pieces. Okay, I can use midpoints. I'm going to skip that piece. 5 subintervals. 1, 2, 3, 4, 5. Got that. They have to be of equal length. So from 0 to 6, that's a delta x. That was 6. From 6 to 12, delta x is 6. Looks like they all have the same width. That's looking pretty good. So meets that criteria. Next piece it says is I must use midpoints. What that means is when I take f of x times delta x, I don't want to use the left-hand value for my f of x, or the right-hand value. I want to use the middle value. So for this first rectangle, the delta x is going to be 6. But my f of x is going to come from the middle point. The middle point between 0 and 6 is 3. And for this equation, that is 7.5. So to find the Riemann sum, I would take 6 times 7.5. For the second one, same process. My delta x is 6. The midpoint of this one, so it goes from 6 to 12. The middle of those two is 9. So if it asks me what my f of x is, I need to choose f of x being f of 9, and f of 9 is 12. So I do 6 times 12. And I keep doing this for all 5 subintervals. Make sure when you get your final answer, the last piece is to use the correct units and explain the meaning of this integral. That's a big detail that some people will miss, and I know it's going to happen. And when it does, I'm not going to feel sorry at all. Because if you do all this work, you will get an answer. You'll have 5 values for all 5 subintervals. You want to make sure to add them together. That's why it's a Riemann sum. This is the Riemann. The Riemann sum is to add all 5 of them together. And then make sure to use the correct units. So if we are integrating velocity, when you integrate velocity, you should always get a distance of some kind. Make sure to note the problem, which distance that's going to be, whether it's in feet or centimeters or miles or whatever it's going to be in. Make sure you know what that is. And then part B, find the average acceleration. Average acceleration was a formula we had in the book. Make sure to look it up. If you're trying to find an average of any kind, make sure you find that from that piece. So there we go. That's the entire test. I wasn't able to do any individual ones because that wouldn't be fair to those people that have indexed this for those that don't, but I hope I gave some explanations on where to start on a lot of these, or some similar examples to them on other problems. So you have starting places for most of these, and the ones that you don't, you have a similar example too. I hope this leaves you guys in a good place, and that your test is able to be finished by tomorrow night. I will be posting a video tomorrow. I'll post Wednesday, Thursday, Friday this week, and that'll be it. Hope you guys have a good rest of the day. Good luck on your test. And remember, it is due tomorrow at midnight, and I will see you guys then.